actually put all my recordings and lectures also. Okay. So just go through my folder in the shared drive, and all the lectures are available to you. Okay. So here, now the recording has started. So we introduced this parameter modulation index, which we are going to discuss now in detail. And then we have another parameter, which is called the peak frequency deviation data, which is KFVM. And how my frequency is changing from FC to something else is given by this modulating frequency, which I put in the. So this is a summary of what we learned in last lecture. And we have done certain examples based on that. So coming to the modulation index, which we have to understand, and we'll do some supporting examples also side by side. So let's understand these two parameters, KF, VM, MF, modulation index, P frequency deviation, and so on, or deviation constant, how they are related to one another. Let's try to understand this thing more logically and in detail in today's lecture. So let's start with the modulation index, because we are just talking about frequency modulation index. So we'll put it as frequency modulation index. Only thing, we are changing MF, MA, and all those things. So this is obviously with respect to the frequency only. So how this we define the modulation index here, which we have to understand. So it is defined as MF, if I have only a single frequency, as delta over FM. Okay, that is very important. So this is given by this thing. So there is a relation between what we have learned, the delta part, which is here, KFVM. Now, if you notice here, delta is given by KFVM. So if I substitute this thing, so I can also write down as KFVM over FM. So because this we have learned already, that delta is nothing, it is KFVM. So this is the simple modulation index. If we define, delta is the frequency deviation, so that means it is in Hertz only, and this this is also in Hertz. So basically it is a no units, Hertz by Hertz. So it is basically no units, just like we have in the case of AM modulation index. And as I said, KF is also having the units, some different units, which you have seen. So in this case, also the units are matching on the both the sides. But important points to note here is that MF can be greater than 1, unlike at the unlike in AM, the maximum value could be 1. Otherwise, it is not desirable. So basically, it is between AM was it is between 0 and 1 only, 100%. So it is greater than 1, and there is no theoretical limit. No, it can go any value. It can take any value. No theoretical limit. So it can take anything. Also here, if we have seen that last time, we have seen that if I increase the amplitude, it will result into overmodulation and so on. But here it is not, it doesn't happen like that way. So if I increase the amplitude or frequency, sorry, okay, of my message signal, okay, there we have seen it will give rise to the overmodulation, but here it doesn't result into overmodulation, and that is the biggest advantage in FM. But there is another interesting thing to observe here, which we'll see also. It does increase the bandwidth. Bandwidth increases. There my bandwidth remains the same. It is always given as twice of FM. Okay. So bandwidth there always remains as twice of FM, or even the case of a single sideband, it is simply FM. So it doesn't increase the bandwidth. But here it does increase the transmission bandwidth. That is important. How? We'll just see some examples, what we have learned, that your MF could be greater than 1 and so on. So let's take one example based on that. So I have the example like this. So I have a FM broadcast transmitter, which we normally use, 88 to 108 megahertz. So transmitter we typically write as TX and receiver as RX always. So I am using a short form, and in the future lectures I will use TX or something. Okay. Let's say it is typically, because these are the typical examples, that means the same values we normally operate. So it operates at its maximum, let's say, frequency deviation of 75 kilohertz. This is the typical values. Typical values, you normally use the word typical in the examples. The reason being typical value is close to the reality. Suppose I say typical value of acceleration due to gravity G is 10 meter per second square. So that is typical. It is close to reality 9.8 meter per second square. But I can't say the typical value of G is 200 meter per second square or 1 meter per second square. That is not typical value. So when I use the word typical, please understand that it is close to the reality or real values. And in the examples also, as a good examiner or a good instructor, they always use the word typical values. Okay, so you understand the real life problems. So here I have taken the maximum frequency deviation of 75 kilohertz, which is basically true in our FM radio. Okay, so what is I want to know what is the limits of the, obviously, extreme limits. There are two sides. One is the minimum and one is the maximum. Just like in the case of AM, the modulation index can vary from 0 to 1. So here also I want to know what is the extreme limits of the modulation index. Obviously, we are talking about the frequency modulation index. So that is quite obvious. For I have got a speech signal or audio signal. So that becomes my, because audio frequency range is from 50 hertz to, let's say, 15 kilohertz. Okay, that is my audio frequency range. So this becomes my message frequency. So to solve such problems, it is very straightforward. I need to find the modulation index, which is given as delta over FM. And delta is given as 75 kilohertz, which is, I should write always as 75 into 10 to power 3 hertz. That is always we should follow. So this is what is given to me. Now, what is my modulating frequency range? So FM, which is the message signal, it varies from 50 hertz to 15 kilohertz. So that is something we have to find out. So if I have FM is equal to 50 hertz, your MF becomes, so delta remains the same. So it becomes 75 into 10 to power 3 hertz by 50 hertz. And if you see, I am putting the units also, so you get the idea. So it is 1500. And if I have the other range of my audio frequencies, because as I said, my speech signal could vary from various frequencies, like in an orchestra or so on, 75 kilohertz, this becomes 75 into 10 to power 3 hertz. Oh, sorry, it is 15 hertz it is given. So I put it as 15, and it becomes 15 into 10 to power 3 hertz. So it becomes, so obviously my modulation index varies between 5 to 1500, and it is larger, or I would say 1500 to 5, because that is the way we should speak, because 1500 corresponds to lower FM frequency of 50 hertz. So it becomes from, so it varies. So if you see here, it varies from any value. It can't be from 0 to 1. It can be having a value of 1500 or so. So this is the typical broadcasting station we use, and it is given as 1500s. So let's take one more example, how to what we have just learned so far. So if I have, I need to find again the modulation index. let's say, obviously for the FM signal, okay, for which I have got VC maximum, that means is given as 10 volt. FC carrier frequency is given as 20 kilohertz, and your message signal amplitude is given as 3 volt, and message signal frequency is given as 1 kilohertz, and let's say deviation constant, which is the frequency deviation constant. As I said, when I'm talking about the deviation constant here, it means frequency, which is we typically say as KF is equal to 2000 hertz per volt. So if you recall, in my last lecture also, somebody asked this question, and I am stressing the again in this slide that KF has units of its units are in hertz per volt. So this is hertz per volt, and then volt will cancel, hertz will cancel. So still it has got the same units. So this is, you have, please note that this is very important. KF is a, though we call it is a deviation constant, so but it has got the units of hertz per volt. Okay, that's very, very important. Somebody asked this question, and I am again clarifying this and this because this is something we have to understand. So it is a, though it is a constant, frequency deviation constant, as we have seen in the last slide, KF is your frequency deviation constant. So it is in hertz per volt. That means when I'm changing the amplitude of the message signal, how much my frequency is getting deviated, okay, changed as per the per volt. So this is again stressing that. So I come to that slide. So yes, so we have to find the expression for. So also find FM signal. Not find, but I will say write expression for FM signal. So how to go for this? So it is very clear. Peak frequency deviation is given, which is given as KF into VM. Now KF is given to be 2000 hertz per volt, and VM, the maximum value is given to be 3 volt, and delta, which is we have to find. So delta turns out to be KF into VM. So it turns out to be 2000. Always put the units so you'll never go wrong, because this is a bit confusing, deviation constant especially. So it becomes 6000 hertz. And I have to find the modulation index. So modulation index is given as delta over FM. Okay. Now that means in this case it turns out to be 6000 hertz over 1000 hertz. Okay, so modulation index turns out to be 6. So it is between greater than 1. And therefore, my FM signal can be represented as VFMT is VC sine 2 pi FCT. Okay, that is we have learned, plus MF sine 2 pi FMT. That is the expression which you have seen and recalled in the first lecture, first slide. So this is the one I am using, this one, MF is this thing. Okay. So cos and sine, they are interchangeable. That doesn't matter much, because how you start the initial expression, it could change. So it could be cos and sine and sine and sine. So that should not be a problem. So not to worry about this sine and cos things. That depends upon how you express your message signal in terms of sine or cosine, but both are sinusoidal function. So in this case, my VFMT could be straightforward written as 10, because VC is given as 10 volt. And please note that it is always in volt and so on, never in kilovolts. So we always work in terms of hertz, volt, and so on. So it becomes, so sorry, this was something like this. Let me see. I have not done that mistake in that first slide. Here it is fine. Okay. Okay, so it becomes 10 sine 2 pi fc. So fc is given as 4,000, 2,000. So it becomes 40,000 pi t plus 6 sine, and fm is given to be 1 kilohertz. So it is 2,000 pi t. That's how we do the problem. Okay, so that is the parameter. So please note that the frequency deviation constant has got the units of hertz per volt, and modulation index doesn't have any unit, which is given as delta over Fm. Okay, so these are the three expressions that we talk about. Okay, MF, KF, and that we have learned. Now there is another parameter which I want to introduce besides KF and MF, which is the delta F. Okay, now that is very important. Why? What is this delta F? So I introduced another parameter, which is what we call the instantaneous frequency deviation. What that means? So what we have learned is, again, just for your confusion, I am writing this thing because these are various terms which could be a bit confusing. We have learned about KF, which is my frequency deviation constant. Okay, I'm just writing it again. Frequency deviation constant, because these are the various terms quite related to one another. And then we talked about delta, which is what we call the peak frequency deviation. Okay, so this is the another term which we call the peak frequency deviation. Peak frequency deviation, that means how much the frequency is changing. So it is given in hertz, and as we have seen in the previous example, this is given in terms of hertz per volt. And then we have the modulation index. So this is the three terms which we have understood. So it has got the no units, and we have seen the relation between them also. Now here I introduced, so this I'm putting as recall, which I learned. So we introduced a parameter, what is called the instantaneous frequency deviation. KF we have learned, it is deviation constant. So we introduced a parameter which is called the deviation sensitivity. Deviation sensitivity. Because we have seen how my frequency is changing. It is changing with respect to the amplitude of the message signal. And amplitude is measured in terms of the volts. So how sensitive? That means with minimum change in the voltage, how much minimum frequency is deviating. So that is what we call the deviation sensitive. Sensitivity means if you change the one parameter with a very small amount, how much it will change, or big amount, how much it will change. So that is what we call the sensitivity. So deviation sensitivity, so introduce this parameter. Obviously, as I said, it is also called the frequency deviation sensitivity, and it is written as delta F. So please note that there is a small difference between the capital, this is the Greek delta, capital delta, and that the peak frequency deviation, which is in hertz, is a Greek delta, but small Greek delta. Okay, so delta F is given as KF into Vm. And this also is also given as you have seen, KF into Vm. Can you see the difference? Can you see the difference? This is a capital Vm. Okay, so this is something which I want to highlight. This is small Vm. So here my Vm is, I would say, instantaneous amplitude, that at every instant, because this is like your it depends upon the T of modulating or message signal. So obviously this also has got the unit in Hertz, but the one thing, so I put all these three terms together in one slide. The reason is I want to stress this important thing. And that important thing I am highlighting. This is in capital and this is in small. So that is maximum or the peak amplitude, as you have seen in the previous example. And obviously its unit is also the, that means how much my frequency is deviating, the maximum frequency. And this is the frequency deviation sensitivity. That means how much my frequency is changing or deviating at every instant. Okay. So this is what we call the uh, this thing. So it is very important that your instantaneous frequency deviation is directly proportional to the instantaneous amplitude of the modulating signal. Okay, so this is what we call the, or sometimes it is also called the, I put it in the black color only, simply the frequency sensitivity of FM. So it is one and the same thing. So these are the two parameters which we call. So one and the same thing, what we normally known as deviation sensitivity, but it is also the frequency deviation sensitivity. Okay, so this is what we call a frequency deviation sensitivity. Delta F is capital delta rather than the small delta. Small delta has is directly proportional to the maximum amplitude of the message signal, and capital delta F, which is my deviation, is proportional to the small Vm, that is the instantaneous value. Okay, so this is what we call this thing. So that means your instantaneous frequency deviation is directly proportional to the instantaneous amplitude of the message signal. So I will just put it here, what we have learned here. I'll put it in the black color. Oh, sorry. What I put it here? Or what was the word I was used? Frequency sensitivity of FM. Okay. One student has sent me the email last time that my writing is not legible. So please understand that I'm speaking also. I would have given you these slides, but I don't understand that will help a lot unless I write and you write. So because I am also speaking and writing on an iPad, and writing on an iPad is a bit difficult as writing on a with a chalk and or a pen on a paper because it is very, very sensitive. Sensitivity is also here important. So sometimes I just mistakenly put more pressure, it changes the slide and so on. So please bear with that. And I'm speaking also, so please listen to, and I'm sharing the recording, please. But as I said, also I suggest to you that you also write simultaneously, and then it will help you. Then no other book is required or nothing. You can look to anything in the Google, other things. Okay, so this is what we have learned. So it is also expressed in terms of uh, uh, the deviation constant. So what is the unit here? It is in terms of the Hertz and so on, because this is Hertz per volt multiplied by volt. So it becomes Hertz only. And obviously it is clear how much it is sensitive is this one. Okay. Okay. Then we introduce another parameter. So yes, I forgot to write one thing. It implies, what it implies that your frequency deviation is directly or linearly proportional to the amplitude of the instantaneous amplitude of the message signal. So please note that this is the word instantaneous amplitude. Okay. I think now these things become most clear. What is the maximum amplitude? What is the this thing? And let me see. So another one thing I wanted to produce here, if you again we recall, sorry, again I recall what we have learned so far, just to put in one place, delta is equal to Kf into Vm, capital Vm. Okay, and also we have learned your MF is equal to delta over Fm, which means delta is equal to MF into Fm. Okay, now we have two expressions for this one. So delta could be expressed in terms of KFVM, and also delta could be expressed in terms of MF, FM. So that is how these two things are related to one another. Okay. Now, just like we have the percentage of modulation in AM, which was very simple. Whatever modulation index you got it, multiplied by 100, that gives you the percentage modulation in the FM, AM. But what is the percentage modulation in FM? So it is slightly different. So if I have to express in terms of percentage modulation in FM, it is a bit different. So we defined as is equal to delta F, sorry. They are very straightforward, no derivation, nothing. Actual over delta F, what I would say standard. What is the standard? I will explain to you into 100%. What it means? What are these things? Like delta F actual is equal to the actual frequency deviation. Okay. Actual frequency deviation, which is obviously in terms of the Hertz. And delta F standard means what is allowable. Okay. Is the maximum frequency deviation allowed by the standard of FM broadcast communication system. FM is basically used for the FM broadcasting communication system. Like for example, it is equal to plus minus 75 kilohertz for commercial FM radio. That means my maximum deviation is allowed from to vary either plus minus 75 kilohertz. My FM frequencies, if you recall, FM frequencies are from 88 to 108 megahertz. That means each station has been allocated a frequency, like radio which has been allocated in 98.3 megahertz, which we normally know because we hear it quite often. So that means 98.3 megahertz plus minus 75 kilohertz is allowed. So what will happen here? Now there is no chance of splattering, because in the case of AM, if it exceeds 100% modulation, then we have a chance of over modulation or splattering. That means the signal going to the nearby channel, next channel, adjacent channel. But here, because we allow that thing, your percentage of modulation is with respect to that, it can't deviate so much that it goes to the next this thing. So this is the various terms which we have understood. So especially the first slide and this slide, which is I'm just showing it to you right now, are very important. It is something like we introduce various parameters and how they are related to one another. Okay. Now here I introduce one more parameter, which is also equally important, but this is the last parameter, and that is what we call the deviation ratio. Okay, it is not that useful parameter, but it is something which we also understood that it is also equally important. So that is what we call the deviation ratio. So I just bring that one, deviation sensitivity, which we have just understood, which was KF and deviation ratio, which we normally say DR. So just recall what we have learned in the last slide. Your delta F is equal to KF into VM, okay, or your deviation sensitivity is KF is equal to delta F over VM. That means it is in Hertz per volt, okay. And we define, so deviation sensitivity is defined as the ratio of the instantaneous frequency deviation to the instantaneous amplitude. So again, I put it as here. What is delta F? It is the instantaneous frequency deviation, which is in Hertz, and VM is nothing. It is the instantaneous amplitude of modulating or message signal. Okay, so that is something which we are, so this is the last parameter which we are going to discuss is deviation ratio. So we define deviation ratio, which is DR, as DR is equal to delta over FM. So this is the difference between the deviation sensitivity and deviation ratio. So it is defined as the, what is my delta? It is defined as the ratio of the peak frequency deviation that we have understood, delta, okay. And this is what we call the maximum frequency component present in the modulating signal, okay, which we have also expressed as the signal in the first slide, if you recall. If you recall, we have in the first slide, I moved to that slide, 7, 6, 5, 4, 3, 2, 1. This one, this expression, F of FMT is equal to, which I put it in the this red box. So here, this is the last parameter which we have to understand. It is not very popular. Other parameters are very important, but yes, this is also an important parameter because it is also called the worst case modulation index, because sometimes we have to find out what is the modulation index which could go worse, like in the case of, so this is also sometimes called the worst case modulation index. That is the worst case it could be possible, that it is too much this thing. Let's understand by our FM radio, what is this deviation ratio is quite significant and what is the worst case and so on. So let's me understand. So what is the significance of this? Basically, as I told you, significance is this. It will tell me what is the worst modulation index. Like in the case of AM, it is 1. Over greater than 1, it is given rise to a modulation. But in the frequency modulation, as I said, modulation index could vary from any value to a highest value. So, but highest value, there are also some worst case. So let's understand by simply our commercial FM radio. So I take the example of commercial FM broadcasting system, FM broadcasting radio system. Okay. Here, as I said, maximum frequency deviation is, as we have seen, is given by 75 kilohertz, which we have just taken an example. So that is the thing which you have seen. It is typically specified as a standard plus minus 75 kilohertz. Okay. And maximum modulating signal frequency is, which is my, normally we in FM also, maximum speech is the broadcast. TV is different. TV, I am also allowing video to broadcast, and video has a much larger frequency. But in AM and FM, the broadcasting is the speech or the orchestra or musical instrument that we are playing. So it is always, it is 15 kilohertz, as I said, we have seen in the previous example. So that is as a standard we have taken this as by the standard of the FM broadcasting system. Therefore, for in this case, your DR, which is given as delta over FM. So this is my delta, and this is my FM. So it turns out to be 75 kilohertz over 15 kilohertz. That means for the FM radio, your worst case um, modulation index is 5. And that is this thing. That means at this point, your bandwidth is maximum. Okay. And after that, no further increase in the bandwidth. So it means, it implies that, so this is just an example. So when modulation index of FM is 5, the widest bandwidth is possible. Because if you recall, I said, and I will also explain to you right now, as I just told you that in the case of AM, my bandwidth remains the same. It is twice of FM. But if you see, when I was talking about the FM, I say, here my bandwidth will go on increasing. It increases the transmission bandwidth. It increases the transmission bandwidth. Modulation index. Just recall that slide. Just recall this slide, which is very, very important to understand. Where is that slide? It does increase the transmission bandwidth. That's very important. But how much? If I need large bandwidth, it will become very, very costly. So there is a limit to increase the bandwidth. And this limit is again decided by the standards. Like for FM radio, it turns out to be 5. That means the maximum bandwidth will occur when I have a transmission modulation index of 5. So it occurs. And beyond that, there is no further increase the bandwidth and so on. So that is the worst case modulation index. I don't want to exceed so much bandwidth that it overlaps the other signal and so on. So this means when the widest bandwidth also occurs, oh, sorry. So this is the deviation ratio. Okay, so deviation ratio clearly indicates that it will about the maximum modulation bandwidth and so on. Okay, coming to the next part, which is equally important. Just like we have the mathematical analysis of A, which are very simple because there you are multiplying the two sine functions or two cosine functions or two sinusoidal functions. As I said, you can take cos or you can take sine, so these are interchangeable. And we have seen that when you multiply the two sine functions, sinusoidal functions, whether sine or cosine, you always get the sum and the difference. Okay, so I get carrier plus FM and carrier minus FM. So these are the two side frequencies that I get, that I got in the FM AM modulation. Why I'm getting two side frequencies, FC minus FM or FC plus FM? Because I am multiplying the two frequencies. So when you multiply two frequencies, you are multiplying the two sinusoidal function, sine FMT and sine FCT. You multiply this, you get the as a sum and a difference. So we got the bandwidth dependent on that. But how to do the mathematical analysis or the spectral analysis of the FM wave? So let's talk about the mathematical analysis. Because here it is not that simple as the product of two waves. When we talk the mathematical analysis, it also means the spectral analysis of, because I'm multiplying the two frequencies. So basically I'm working in terms of the spectrum, frequency spectrum and so on. So here also we normally talk about mathematical means and the spectral analysis of FM wave, of FM signal. Okay, how to go for that? Let me put this thing. So yes, I'm trying to put in the simple way. VFMT, what we have done, uh, if you recall that expression, so which we normally use in terms of the modulation index. Now we'll restrict ourselves, is equal to something like this, VC cos, okay, and it was omega CT, okay, plus MF sine omega MT. Okay, so that was my expression. In the case of AM, it was the product of the two functions. Okay. Here, if I use the trigonometric identity, for simplicity, let's take for simplicity, I ignore this thing. I just concentrate on the frequency part, okay, for the time being. So for simplicity, I could write down this as cos omega CT plus MF sine omega MT. I just ignored the this thing, okay. Now, if I use this trigonometric identity, which is given by quantity like this, cos A plus B. This is the form of cos A plus B. And cos A plus B is nothing. It is cos A cos B minus sin A sin B. Okay. If I use this thing, so in this case, this becomes my A and this becomes my B. So in this case, my V of FMT could be written as cos A cos B. So it could be written as cos omega CT cos MF sine omega MT. Okay, that is the first term, minus sine omega CT sine MF sine omega MT. Okay. Now here, if you notice here, it is not that straightforward. Last time we got it simple trigonometric functions, multiplication of two sinusoidal frequencies, but here cos of another sinusoidal function. So cos of a sine of a sine. So here we are getting a different type of function, which is what we call cos of a sine or sine of a sine function. Okay. So this is a slightly different type of the frequency. So normally such things we solve by, so it is like a cos of a cos function or sine of a sine function. Okay. So the problem here is this challenge that I have got the cos of a sine function or sine of a cos function. So how to solve such things? Okay. So this, if you notice here, I am putting here, sorry, not this one, cos of a sine or sine of a sine. I have to close the bracket also here because there are two brackets. Let me write very clearly. So how to solve such things? So this is the challenge. Here it is not this thing. So we solve them what we call the Bessel function. I think, I don't know whether you have learned the Legendre function or Bessel function. So yes, you must have learned in the first year Legendre function and Bessel function. So here these expressions can be expanded in a Fourier series using Bessel functions, which we normally denote as J N MF. Okay. JNF is what we call the Bessel function of first kind and order n, where this n defines the order. So I just put it here. I'm not going into the details of this, but we are simply using this. But in a simple way, I will try to explain, even if you have forgotten. So this is very, very important. To solve such cases where we have a sine of a sine function or cos of a cos function or sine of a cos function or cos of a sine function, we normally solve them using the Bessel functions, J and M, which is we defined as J and M. That means general Bessel function of first kind of order n. And here they are given by, so basically, I will go to the previous slide. I marked this expression as A because this we are going to use. Okay, 1. Okay, so what we do here, I will just write down for you so it will be easy. Equation number 1 can be expanded. So in a simple way, just not to worry about you in case you have forgotten, we normally expand in terms of the Fourier series, okay, using Bessel functions J, N, M, F of first kind and order n. They are different kinds, first kind, second kind, third kind. But here for us, it is more than sufficient for us using the first kind. And that you can refer to any of the books, or I think you must have learned it. But right now, I just simply use what is available in the standard table. So you need not remember also, but it is very straightforward. Can be found in a standard mathematical table. You need not remember those values. It is just a very standard mathematical table. It is, you can find. So no need to remember. Okay. So how I could write down this as equation number 1 can be written as VFMT. And what are these values which are available in the standard table? I will explain to you later on. It's typically given as, in the Fourier series, if we expand, it is given as J0, where 0 is the of order 0, J0 MF, okay, cos. So this is the standard derivation equation. Again, I can write for you. It is given as cos omega CT minus, so that is first expression, J0. Then we'll have expression based on J1. So J1 MF cos omega C minus omega M T minus cos omega C plus omega M T. So this is how we expand this series. And then we'll have second order J2 MF cos omega C minus twice of omega MT minus cos omega C plus twice of omega MT. Okay, so this is how we expand this Fourier series in the Bessel function. So this is a Bessel function which is typically written as like this. And then I could explain one more, let's say, just to make it clear. It becomes very simple. J3MF, again, cos omega C minus 3 omega M T and minus cos and so on. That means if you see here, unlike in AN, which is a product of two sine functions, and because of which you get sum and the difference of the two frequencies. That means omega C minus omega M and omega C plus omega M, omega or F, whatever you call. Okay, angular frequency, it is 2 pi fc. So only two side bands were possible, and my maximum bandwidth was from minus omega C M to plus omega M. Okay, twice of Fm or twice of omega M. But here, if you see, because it is a product of a cos of a cos function or sine of a sine function, not the product of two function, two sinusoidal function, not cos A, cos B, but cos of another sinusoidal function or sine of another sinusoidal function. So then such equations can be, such trigonometric identities could be solved using the Bessel function of first kind and nth order, which are typically given by like this. So if you see here, what frequencies I will get? I have got omega c, I have got my omega c minus omega m, omega c plus omega m, omega c minus 2 omega m, omega c plus 2 omega m, omega c minus 3 omega m, omega c plus 3 omega m, and so on. That means your bandwidth is infinitely large, unlike in the case of AM. But as I said, the widest bandwidth is possible defined by the your worst case modulation index, which we just done, deviation ratio. Okay, but yes, it actually now requires what I said, large transmission bandwidth, which you can say is a disadvantage, because when you have a large transmission bandwidth, the system design becomes more complex. But your noise becomes noise is not that high, because there was over modulation was there, splattering could occur. That means my signal goes to the adjacent channel, which is a noise for that channel, not desired signal. But here my noise is not there, because there is no cause of over modulation, okay, or splattering. But the thing is that here noise, I got the advantage, but it requires a large transmission bandwidth. But you can stop it at, let's say, at some modulation index, which can give me various these things. So I will just explain to you the Bessel function in tabular form, which is typically available, how this thing there. But one thing is clear from here. In my spectrum, I got various frequencies. But how many various frequencies? It is given by the a Bessel function table, which is normally available in any appendix of any book or something like that, but which I will also reproduce for you. So basically what we have understood this now, because it is a, again I am stressing, because it is a sine of a sine function or cosine of another sinusoidal function, we can solve it using the Bessel function. And if I solve in the Bessel function, this is the way the Bessel function are represented. Okay, what you have learned. That means here I will get omega c, the original carrier frequencies, but many side frequencies. Suppose my carrier frequency is 1000 kilohertz and my message frequency is 1 kilohertz. So I will get, say, 100 kilohertz and 1 kilohertz. So I'll get 100 minus 1, 99, 100 plus 1, 101, 100 minus 2, 98, 100 plus 2, 102, 100 minus 3, 97. So many side frequencies will be there. And their amplitudes will also change. How these amplitudes vary? They are decided by the this J0, J1, J2, their values. So those values we can look up the standard appendix tables for the Bessel function, which I will also reproduce here for your convenience. So basically I would say the frequency analysis of FM signal consists of a carrier with amplitude J0 MF. Okay, that is the first term. That is the first term which we got it, J0 MF cos omega CT. Okay. Okay. And then we have side bands spaced symmetrically on both sides of carrier. So here we got the carrier with amplitude J0 MF, that is the first term. And then we get many terms which have the frequency separation of plus minus delta omega m and plus minus, or plus minus omega m, plus minus twice of omega m, plus minus 3 omega m, and so on. And the various modulation index and amplitudes of J1 MF, J2 MF. If you see, that is the amplitude here, J1, J2, and so on, J3 MF, and so on, respectively. So I write it clearly. So basically, just because of this form of sine of a sine, we have to go by the Bessel function, and this Bessel function gives me so many side frequencies and so on. Okay, so the table is something like this. So just no need to mug up this thing. So this is what is available in okay. So this is from the available in appendix of the books. Okay, so no need to remember. This is for your understanding. Okay, so it is something like this. I have various values, so no need to remember. Just it will be provided to you whenever we solve the problems. How we solve the problem, that we'll understand. So if I have the various values MF, then J0, MF will be what? J1, MF will be what? J2, MF will be what? J3. And let's say J4 MF. So these we take for various values of MF. The various, so these are what we call the Bessel functions and constants and so on. So these are the values that are available. So I can take the MF of 0 also, as I said. For 0, it is 1, 0, 0, 0, 0. And I said no need to remember this, just understand it. I can have MF as 0.5. Again, this could be calculated, but we don't go. This is beyond our scope, but just remember that. It is given as 0.9385, 0.2423. As I said, no need to remember point. But we use this thing for our understanding of the FM in the various examples that we see later on, and so on. And there are many other. So this is like, and JF4 is not the it is still continuing. And then we have, let's say, a case of 1.0. In this case, it is 0.7652. So obviously, these are the amplitudes of my side frequencies. Okay. And amplitude goes on decreasing. Unlike in the case of AM, we got only two side bands of the same amplitude. Okay. So here, my amplitude basically goes on decreasing because of this Bessel function. So it is now reduces to 0.4401. It is 0.1149. As I said, this is standard table of Bessel function. So no need to remember. So I got this, and then it will go on decreasing. Let's take one more example of one we have taken. Let's say 1.5, because we are going to refer this for solving our problems. And normally these things are provided. 0.5579. And this is 0.2321. I am also referring to the table. I could also 0.0610 and 0.0118 and so on. Let's take one more up to 2. 2 is 0.2239, 0.5767. I particularly took this case. 2, there is another reason for that. 1289.034. That if you see here now, it has increased. In J0 is 0 and J1 has become much more than the J0 value. So that is also possible. And also one more case I took, which is, let's say, 2.5. Again, the reason is something different. It is minus value, 484. So it will become minus sign here. And then it has increased to 0.4971. and then it again is decreasing as 4461, and then here it decreases 0.2166, 0.0738, and there is another value which you will get after that. It is 0.00195, so another which is J5 value. So if you see here, what I stress that these coefficients are calculated by some standard Bessel functions, so no need to remember. So there is a possibility that it increases from 0.58 to 0.79 or 0.27. So that is a possibility. It could increase also, and there are certain negative values also. So negative values means in communication system, negative value means your phase changes. Okay, as I said, frequency and phase modulation are related to one another. We'll discuss also slightly more in this way. So my phase will change. That means from 0 to 180 or 180 to 0. So my phase will also change. So negative sign implies here is this one. Okay, so this is my spectrum. We'll understand this spectrum more clearly in my next lecture and take some examples to understand this. So basically, I will not recall everything, the various parameters that we've learned, put it in all one place. But the spectral analysis or the mathematical analysis, I want to stress that again, before closing this lecture, that in AM we have the product of two sign functions, sine A, sine B. So it gives rise to the sum and the difference. So we get only two frequencies, two sidebands, and with the same amplitude. And we have seen that carrier is not carrying the information. So we could suppress the carrier, which is called a double sideband suppressed carrier. Or then we have got for the single sideband that even both the information, same information is contained in the both the sideband. So if I can reduce one of the sideband also, my purpose is solved. So there we have only two side frequencies, we get it in normal AM, conventional AM. And my bandwidth is defined as twice of that. But here, because it is a sine of a sine function, so we can't solve a simple trigonometric identity. We have to use the Bessel function to solve such trigonometric identities. And Bessel functions are defined by this relation. That means it will give rise to carrier plus number of the side frequencies, omega c minus omega m, omega c plus omega m, omega c minus 2 omega m, omega c plus 2 omega m. And their amplitudes are given by this Bessel coefficients. So these, what I'm writing here, are basically the Bessel coefficients. And they are calculated for various values and put it in a form of a table. Put it in a form of a table or even a graphical form also. Some books just refer to the graphical table and so on, which I will also put in the next slide. But these graphical form or the tables are available for you in the appendix. No need. What in my appendix we have learned how these values have arrived, but here we will apply those things. Okay. So this is the only thing we need from the Bessel function point of view. And we will understand this thing to how to calculate the bandwidth, how many side frequencies will be available, and so on. So that will continue in my next lecture. I will stop the recording, but before that, any questions? Any questions? Okay. No more questions in the chat box. So I stop it here. Save this file as PDF and share the recording also with you. PDF file will share it immediately. Recording takes some time to get processed, so that we'll do later on. So I stop it here and we'll continue with this in the next lecture. No more questions. Okay, fine.